most valuable forensic sources in a memory image. Every active TCP connection, every listening socket, every UDP endpoint all leave structural traces inside the Windows kernel. This volume teaches you to extract, interpret, and correlate network evidence from raw memory dumps without touching a single packet capture. Windows manages network connections through the TCP/IP kernel driver, pip.sys. When a connection is established, Windows allocates a kernel object tracked by pool tags. Active connections use the tag TCPT for TCP endpoints and UdpA for UDP endpoints. Closed connections leave behind TCPe objects partial records that persist in the pool until overwritten, making them invaluable for timeline reconstruction. The core structure for active TCP connections is _TCP_endpoint. It records the local and remote IP addresses, local and remote ports, the connection state, the owning process ID, and a creation timestamp. On Windows 7 and later, this structure also links to the process's socket handle table, letting you correlate every connection directly to the responsible process without any guesswork. UDP endpoints are tracked by _UDP_endpoint structures. Unlike TCP, UDP is connectionless, so there is no remote address or port stored, only the local binding. However, the structure still records the owning process, the local address, and the timestamp when the socket was bound. Malware using UDP for beaconing or DNS tunneling leaves exactly this kind of artifact in memory. Listening services are tracked by _TCP_listener objects, distinct from active connections. A listener records the local port, protocol family, the owning process, and the interface it is bound to. Binding to 0.0.0.0 on an unusual port is immediately suspicious. Backdoors frequently open listeners on high-numbered ports. Netscan surfaces all of them in a single pass. The Netscan Volatility plugin performs pool tag scanning for TCPT, UdpA, and TCPe tags simultaneously. It recovers active connections, UDP bindings, listening sockets, and recently closed connections in one output. Unlike the older Connections plugin, Netscan works on Windows Vista through Windows 10 and handles both IPv4 and IPv6. It is your primary tool for all Windows network forensics. A critical distinction in network forensics is active versus closed connections. Active connections show current state established, listening, or close_wait. Closed connections recovered from pool memory show the previous state and retain their timestamps. A connection to an unusual external IP that closed seconds before acquisition is often more suspicious than anything currently active. Always examine closed records. Windows Vista and later support dual-stack networking. A single socket can handle both IPv4 and IPv6 connections. The _TCP_endpoint and _UDP_endpoint structures include an address family field, AF_INET for IPv4 and AF_INET6 for IPv6. Malware increasingly uses IPv6 for C2 communication specifically because many monitoring tools and firewall rules ignore IPv6 traffic by default. Rootkits can hide connections by unlinking socket objects from kernel tracking structures, the same DKOM technique used to hide processes. The Netscan pool tag scanner bypasses this by reading raw physical memory. However, sophisticated rootkits can also corrupt or zero out pool headers. When Netscan and netstat disagree on a live system, the discrepancy is the evidence. Correlating network connections to processes is the most powerful step in network forensics. The _TCP_endpoint structure stores the owning process ID directly. Cross-reference every suspicious external connection's PID against your PIS list and scan output. A connection owned by a PID that does not appear in PIS list is a DKOM hidden process maintaining a live network channel. Command and control channels leave recognizable patterns in network artifacts. Beaconing malware creates and destroys connections on regular intervals. Look for the same remote IP appearing repeatedly in closed TCPe records with consistent spacing. DNS tunneling appears as high-frequency UDP traffic to a single external resolver. HTTPC2 appears as repeated short-lived established connections to port 80 or 443. Port analysis is a fast triage step. Well-known service ports bound to unexpected processes are immediate red flags. For example, port 443 owned by a process other than a browser or web server. High ephemeral ports opened by system processes are equally suspicious. The netscan output includes the owning module name, allowing instant visual triage without cross-referencing PIDs manually. Memory sometimes preserves partial packet data adjacent to socket structures, fragments of TCP payloads, DNS query strings, or HTTP headers stored in kernel socket buffers. These are not accessible through netscan, but raw string extraction using bulk_extractor or manual carving around the _TCP_ endpoint address can recover request URIs, C2 command strings, and even partial credentials from clear text protocols. The detection matrix for network forensics, unlinked connections versus netscan pool scan detects DKOM hidden sockets. Connections to unknown external IPs correlates with process ancestry via STRI. High-frequency closed TCPe records with a single remote reveals beaconing. UDP traffic to a single resolver with large query sizes reveals DNS tunneling. Unusual port bindings by system processes reveals backdoor listeners. Your Vol.5 command toolkit, netscan finds all TCP and UDP artifacts. Netstat-netscan diff reveals hidden connections. Connections works on Windows XP and 2003 memory. SockScan recovers legacy socket structures. Use bulk_extractor for string carving around socket addresses. Combine netscan output with P's list, scan, and command line for full process to connection attribution on every suspicious endpoint.